This video is to serve as an introduction to electric fields. Electric and magnetic forces, which we'll be discussing in this electricity and magnetism unit, are similar to gravity because they're all long-range forces. They don't require any contact. So to help our understanding of electric and magnetic fields, we'll first discuss gravitational fields that surround a mass. An object that is located near the surface of the Earth will experience an acceleration due to gravity. The acceleration due to gravity is equal to the gravitational force divided by the mass. Or more commonly seen, the force of gravity is equal to m times g. Even though there is no contact between the object and the Earth, there's still a force or action at a distance. The acceleration due to gravity, g, can be referred to as the gravitational field, which is produced by the Earth's mass. The term field really comes from mathematics. It really defines a function that assigns a certain value to every point in space. And since the acceleration due to gravity, or the gravitational field, is a vector, this is really known as what we call a vector field. That means our gravitational field has a magnitude, or strength, and it has a direction. For example, in this scenario where you see the Earth, and we look at a small section where it's relatively flat, then the gravitational field strength has a value of 9.8 meters per second squared and is directed down. So if we were to write this as a field vector, this would be the magnitude and direction shown here. The gravitational field can be shown in this diagram as these field lines. So what we're showing is kind of a gravitational field plot. So for this relatively flat section part of the Earth, we can see that the field lines are of constant magnitude. And this is shown by the equal spacing between the lines. And has a constant direction. They're all parallel and pointing downwards. So hence we say that this gravitational field is constant or uniform. But in reality, if you were to look at the Earth from outer space, well, the field lines are not constant. Here you can see that the gravitational field lines are all pointing radially inwards. You'll notice that the field lines are closer together near the surface of the Earth, which indicates a stronger field. And as you move away from the Earth, the field lines are further apart, which indicates that the field strength is weaker. Similarly, a charged object modifies the space around it and creates an electric field. Just like gravity modifies the space around a mass and creates a gravitational field. The electric field, which is denoted with the symbol capital E, is defined as the amount of electric force per unit charge. The SI units for electric field are in newtons per coulomb. So just like gravity, the electric field has a magnitude, which is equivalent to the force per unit charge, and a direction. They're similar but different. For example, gravitational field is defined as the gravitational force per mass, whereas the electric field is the electric force, which is similar, they're both related to force, but it's divided by the charge instead of the mass. And another similarity you're going to find as well is that gravity is always attractive, but electricity can be attractive or repulsive. Both of them basically modify the space around them. For example, in a gravitational field, the mass modifies the space around it and creates a gravitational field. For a charge, it modifies the space around it and creates an electric field. So how do we test to see if there is an electric field at some point in space? Imagine you have some charged object. We'll just call this the source charge. This is the charged object that is basically modifying the space around it to create an electric field. Well, to test it, we need to probe with something, and we probe with something called the test charge. Our test charge is assumed to be positive. If the test charge at that particular location in space experiences no force at all, then that means there's no electric field. There's zero electric field at that particular location in space. However, if this positive test charge were to experience a force, repelling it to the right, it would move away from this source charge, and it would move in the same direction parallel to the electric field. So the direction of the electric field is in the same direction as the electric force for a positive test charge. Sometimes it helps to understand this by showing the electric field lines that are surrounding a source charge. So here we have a positive source charge that is creating electric field lines that are radially outwards away from this source charge. And then we have the positive test charge within that field, and you can see it's experiencing a force to the right because it is repelling this positive surface here, and the electric field is in the same direction as this electric force. If you were to calculate the electric field at that particular point in space, you would use the formula, the amount of force divided by the charge of this test charge. Now if a negative source charge, you can see all the negatives here are shown, were to be used instead of a positive source charge, we would see that we now have electric field lines that are going radially inwards. So that if we were to probe with a positive test charge, it would be attracted towards this negative source charge, and we would see that the force again is in the same direction as the electric field. And if we were to calculate the electric field at this particular point in space, we would use this amount of force divided by the charge of that test charge, Q. Now, you might be asking, well, what would happen if we had used a negative test charge instead of a positive test charge? Well, if this would be negative, then the force would be to the left, yet the electric field would still be to the right. So the difference would be is that the force and the electric fields would be anti-parallel to each other in the opposite directions. So, in essence, the electric field direction is defined for positive test charges. You could use negative test charges. The difference would be is that the electric force will be in the opposite direction of the electric field. So hopefully you have an idea how to calculate the electric field and have a general understanding that these source charges modify the space around them to create electric fields. And furthermore, you could calculate the electric force by simply rearranging and taking the charge of that test charge and multiplying by the electric field strength, just like we did when we calculate the electric or the gravitational force, which was equal to m times g. Same idea. Okay, I think you're ready to tackle on some problems now.